This video is the second in a series of videos on networking. I'm covering some really core concepts in networking to help everybody get up to speed if you're working in tech or if you're working in cloud computing. So this video, I'm going to cover IP addressing, we're going to look at subnetting, we're going to look at VPC addresses, network address translation, and more. Now, it's important to understand IP addressing. So we talked about the OSI model in a previous lesson, and so you know that network addresses, IP addresses, are at layer 3 of the OSI model. So an IP address looks something like this. So this web server has an attached network interface, and that interface has an IP address. This one is a public IP address, so it can be used on the internet. So IP addresses are the addresses computers use to communicate at layer 3 of the OSI model. Here we have a client. Now, the client computer is the computer you or I might use in order to connect to the web server. And to do that, we're going to use a web browser. The web browser uses the HTTP protocol, and we need to enter a DNS name. Now, we could use IP addresses, but it's hard to remember lots of IP addresses. It's easy to remember Amazon.com, Netflix.com, and so on. Now, what needs to happen is because the computers communicate using IP addresses, not domain names like example.com, microsoft.com, etc., the computer needs to find out the IP address that corresponds to the domain name that we put into our web browser. A DNS server is responsible for that. That's a domain name system server. DNS servers have lots of addresses in their database. So essentially what happens is you type in Amazon.com, your computer goes and speaks to a DNS server and says, what's the IP address for Amazon.com? And in its zone file, it will have an answer, or it recursively connects with other DNS servers to find out what is this IP address we need. And it all happens very, very quickly. So the client connects to the DNS server, finds out what the IP address is, in this example for the example.com domain. Then once it knows the IP address, the connection is made to the web server using IP addresses. So of course, on the internet and on internal networks within companies, within your home, IP addresses are very, very important. Now, IP addresses are written in this format. This is what we call dotted decimal notation. So we've got 192.168.0.1. Each part of the IP address is a binary octet. That means 8. So 8 bits are associated with each component of the address. Why do we have these bits? Well, they are used by computers to determine the actual address that we see in dotted decimal notation. So it's like there's another layer of translation. We've gone from domain names to IPs, and then each part of the IP is actually a binary representation as well, which the computers know. So how do we know what the address number is in decimal based on the binary, so the 8 bits that make up that individual number? Well, you can see here in this example here, or this table that I've put together, we've got different values. So the ones at the top here, they represent the bits that make up this decimal number here. Now, the actual value associated, if this is a 1, is 128 if it's on the left, because that's the most significant bit. And the value is 1 if this is a 1 for the least significant bit. Now, if this is not a 1, it's a 0, then it's 0. That's it. But if it's a 1, it has a value associated with that 1, if you know what I mean. So think of this as an on or off. 1 means on, and if it's on, then one of these values is associated with that bit, depending where it is in those 8 bits. If it's off, then it's a 0, then no values are assigned. So let's have a look at some examples. So the 0 here would just be all zeros. So it's 8 zeros. 1 would be all zeros except for the very last one, because when that switch is on, when that bit is on, the value is 1. Here we've got 192. Well, 192 is 128 plus 64. So it's 1, 1, and then all zeros. And then here we've got 168. Well, that's 128 plus 32 plus 8, and then the zeros in between. And that gets us to the 168. So that's how we can understand binary as well as decimal. And this is important to know, by the way. Now, the IP addresses are broken into 2 parts, the network ID and the host ID. the network ID is the same for all computers on that network. The host ID is different for every computer on the network. Now, how do we know which is the network and which is the host piece? Well, that's where we have this thing called the subnet mask. So it's another dotted decimal number which determines which components of the IP address are the network number versus the host number. So the 0 here is the host ID. All of those bits, those 8 bits that are in this last octet, are available for assignment to computers in this network. Whereas these bits, the 255, masks those decimal numbers and means that they're going to be the same for every computer on that network. So the subnet mask is used to define the network and the host ID. So here we have a network with a subnet mask. Now, I mentioned it's important to understand the binary, and this is why. This is really the main reason why we need to understand the binary, because we often represent the subnet mask in bits. So 255, 255, 255. Now, if you added up all of the values associated with the bits when they're on, so when they're 1, so you've got 8 ones, the values would add up to 255. So 255 basically means that entire decimal piece is part of the network. So that's mastered out. So 8, 16, 24, we now know that 192.168.0 in this IP address is the network piece. And we've only got this last octet available for hosts. So we would represent that as 192.168.0.0/24. So that's how we can represent the subnet mask. That's the most common way you're going to see it represented. So people will say a 16-bit mask or 24-bit mask and so on. And this is why you need to understand this. So here in this network, you can see all of the computers on this network share the same network portion in blue, but in red, that's the host piece. So they're using bits from the host portion for their individual addresses, which have to be unique for every computer on that network segment. So all computers share the same network ID and have a unique host ID. Now, there are some ranges of addresses which are reserved for private use. These are the addresses that are reserved for private use according to the RFC 1918 specification. So these are the network addresses that we're most commonly using for internal addresses. So we can't use these on the internet. These are not valid on the internet at all. They can't be routed to over the internet. They can only be used on internal networks. So that's the way that we will use those. Now, an IP address has 32 bits in total because we've got those 4 octets. IP version 4, that's the protocol we've been talking about, has approximately 4.3 billion addresses available. Sounds like a huge number. It's just not today. With the amount of systems that we have connected to the internet, we have smart devices, we have anything from phones to tablets to computer systems to fridges to car sensors, all sorts of different devices, one IP address is on the internet, and it actually poses a problem. So they're actually close to exhaustion, and this is really something that's been said for many, many years. So we have to use something called network address translation, which we will cover shortly. To solve this, many years ago, they came up with an IP version 6 addressing scheme, which is perfectly valid and usable today. Many systems on the internet, like those smart devices I mentioned, would be using IPv6 addresses. These are 128 bits long, and they're written in hexadecimal instead of dotted decimal notation. So they're kind of hard to remember, much harder than IP addresses. Now, this is the number of potential addresses that could be used with IPv6. And apparently it's enough to assign more than 100 addresses to every atom on Earth, which is just insane. So it's a really huge address space. We can use IPv4 and IPv6 addresses in AWS, for example, in a virtual private cloud. Now let's go back to IPv4, and we're going to start coming up with a schema for our subnets and our CIDR blocks that we're going to use in a VPC. So the VPC CIDR block, that's classless inter-domain routing CIDR, which essentially means we have the ability to subdivide the address space according to our needs. So rather than there's this traditional class A, B, and C, which really is not used much anymore, that's different ranges of addresses. What we do these days is classless inter-domain routing. We use subnetting, and we basically segment the host and the network portions as we see fit for our needs. So for example, this 10.0.0.0 could have a /16 subnet mask, and that means that we can then add subnets underneath that which use part of the host portion, so that we have different networks that are underneath this main block of addresses. Okay, so what we're doing with CIDR, we take one big block of addresses, there's a lot of potential addresses there, and we segment into subnets. So then what we're going to do is, rather than having subnet mask 255.255, we're going to take some of the host portion, because we've got 16 bits here available for hosts. That's a lot of hosts. We don't need that many maybe. And so what we do is we say 10.0.1 is the network number, so it has a /24 mask, so this becomes part of the network ID, and then only the last octet is usable now for hosts. Okay, so how do we work out the right addresses to use? Now, there's various utilities you can use. Again, it's very useful to understand IP addressing quite well yourself so that you can actually determine without using these subnet calculators, but these subnet calculators are super useful, so why wouldn't you use them? Now, this one's solarwinds.com /free-tools/advanced-subnet-calculator. So if you want to find it, that's where it is. So let's actually use this tool, and I'm just going to make this a little bigger for you. So here it's come up with a default number, but I'm going to put in the example that I just showed you before, 10.0.0.0, and that has a 16-bit mask. But then for the subnet, I'm going to use 8 bits. Now that now tells me that means that I can have 256 subnets from this block. So by using this block with 16, but then using a 24-bit mask in my subnets, I can now have 256 subnets. Each of those subnets can have 254 addresses. You can't use the 0, you can't use the last address 255 because that's the broadcast. So you can see the subnets here. It's a great tool because it then shows you what the subnets are. So we got 10.0.0.0.1 with a /24, 10.0.1.0 /24, 2, 3, 4, 5, and so on. And so that tells us the different subnets. So what I would normally do is I would come to a tool like this, and I'd basically be working out, okay, well, how many networks do I need? How many hosts would I like to have in each subnet? And then I can play around with a calculator, and it can tell me which address range, subnet masks, and so on to use. Then I can come back to Amazon VPC, and in VPC here, I'm going to create a new VPC, and I'm going to use that example there. I'm going to use this wizard, the VPC and more, because it makes things a little bit easier. And I'll just call this my networking videos VPC. Now, this actually shows me that exact CIDR block by default, so 10.0.0.0/16. However, what you will notice now, and I'll go full screen so you can see it a bit easier, is when we come down, I'm not going to use IPv6 by the way, when we come down a little further, we can choose the number of availability zones, so 1, 2, or 3. 2 is good for this exercise. You can customize that if you wish to. So you can choose the specific availability zones, which are essentially data centers that you use. I can choose 2 public subnets, 2 private subnets. I can customize this if I wish to. But here I can change the CIDR blocks. It's not using those addresses that we just looked at. Instead, it's using a /24, which gives a lot more IP addresses per subnet. Well, I don't want that many. And I'm going to use just simple addressing where we start with 1 and then we have 2, 3, and 4. So 10.0.1.0/24, 10.0.2.0/24, 10.0.3.0/24, and then of course 10.0.4.0/24. And we're not going to use a NAT gateway right now. We're going to switch off the VPC endpoint. I don't need that. And then it's going to create the VPC for me. And so it does this really quickly. It makes a bunch of API calls and just creates all of the different resources, creates the VPC, it creates the 4 subnets, creates an internet gateway, attaches it to the VPC. So we have a pathway out to the internet, creates the routes in the route table that it created, and so on. So very quickly that's done. If we come back now, we can see I've got 2 VPCs. This is my networking videos VPC, and we can see the CIDR blocks here. You can add more CIDRs if you wish to. We've just got 1, that's fine. And then I'm going to have some subnets. If I just refresh the page here, I've now got these subnets. Let's just put them in a better order if I can. Well, I've got my public 1, public 2, private 1, private 2. And so if I just choose, let's say public 1, you can see the CIDR block 10.0.10/24. Now you notice that there's 251 available IP addresses rather than 254. In AWS, they do reserve a couple more addresses as well. So we've got our subnets, and then of course we've got our route tables. Now, because we're using public and private, we want to separate the route tables. So we've got our public route table. The public route table will have a route out to the internet because we do need to be able to receive and send traffic out to the internet in a public subnet using public IPs. The private subnets are disconnected from the internet completely. So the only route they have is a local route. Now you'll see that we have two private routing tables. We could just have one and associate the two private subnets in the two AZs to this one route table. This gives us a little bit more control though, so that's the default. So we could have separate configurations per private subnet if we wish to, like different NAT gateways that we send traffic to. So these will only have that one route internally, which means if we launch an instance in a private subnet, it is not going to be able to access the internet. It's only going to have a private IP address, not a public IP address. Now, as I mentioned before, IPv4 addresses are in short supply. So what we use is something called network address translation. NAT enables us to be able to access the internet from computers that have private IP addresses, so they don't need a public address on the internet, which means we can share, for example, one public IP address and have hundreds of computers using that public IP address because we do network address translation. So let's have a look at how this works. Now, if we did not use NAT, then let's say we have these computers running and we have a router. The router is the pathway out to the internet, and private IP addresses are being used within the company office or the data center. A public IP address is needed on the router to connect to the internet. In this configuration, computers with private addresses can't communicate to the internet. What would happen if they did? Well, we've got a web server here, so just imagine that a transmission is happening. So the computer here, 192.168.0.2 is its IP address, wants to communicate with the web server. Now, the source address is 192.168.0.2. The destination is the IP address on the internet for the actual web server. Well, let's say, and it wouldn't work, but let's say that the web server actually did receive that traffic. It would then try to send a return traffic. The return traffic would have a destination of 192.168.0.2, which is a private IP address. So none of the routers on the internet know how to get to that IP address. It's not possible. So that doesn't work. The source IP address cannot be routed to. So the return traffic is going to fail. Now let's say that we're using network address translation. Same computer, this one here, 192.168.0.2 is its IP address. It's trying to communicate with a web server. And note that its source address is not this 192 address. It's actually the address of the routing function. It's actually the address of the router, which now has the network address translation feature enabled. So what it does is it swaps the source address. And now the packet goes to the web server, and the return traffic comes back with a destination that is the IP address of the router with the NAT function there. Now the NAT function creates essentially a table, a record of these outgoing communications. It knows where to actually send the packet. So it can rewrite the destination address and forward it on to that computer. So that's how network address translation works. The NAT service takes care of translating back to the private IPs used internally. In a previous video, I showed you VPCs with public and private subnets. And so the private subnets have instances, so this is a virtual server like running Linux or Windows, for example, that has a private IP and it cannot communicate out to the internet. A NAT gateway can then be used for outbound internet access. The NAT gateway is actually deployed in the public subnet, and a route is added to the route table of the private subnet, saying that all other traffic, so everything outside of any specific route, goes to the NAT gateway ID. And so it will forward traffic to the NAT gateway. The NAT gateway will have a public IP, just like this instance in the public subnet. And so it knows how to use the internet gateway to forward that connection to the internet. Let's head back to AWS and I'll show you how to configure a NAT gateway. So back in the VPC management console, I can go down to NAT gateways right here on the left and create a NAT gateway. There is a small charge for running these, so just bear that in mind. I just call this my NAT gateway, my NAT GW. I then have to select the VPC, so I'll select my networking videos VPC, and I'm going to enable it to receive an elastic IP address, which is basically a static public address that's allocated to the NAT gateway, and then just create the NAT gateway. Now, that's all I have to do to create the NAT gateway, but it's not going to work for any instances deployed into the private subnet unless I actually add it to the relevant route tables. So if I come to the private subnet route tables, like this one here, I would then go to routes, edit routes, and I can add one. All zeros is the destination, which means anything else, anything that's not specifically found in the route table before we get there. And then I can choose the NAT gateway. And now I just save the changes, and I have a route in the route table. So now in the instances that I deploy, so if I went to the EC2 management console, for example, I can now launch virtual servers instances. And for example, this one would be a Linux instance. I choose the type of hardware that I want to be available to it. And then I can come down here and choose the network settings. And so now I can deploy this into my networking videos VPC, and I can choose public or private subnets. Now, if I use a public subnet, I'll want to make sure that I enable auto-assign public IP. You can set that at the subnet level as well, so it's always automatic. I haven't got that. The default is not actually enabled when you use the VPC wizard, so we can change that later. Now, also, I can deploy to private subnets, and then, of course, I don't want a public IP address. In both cases, my instances are going to be enabled for outbound internet access. The NAT gateway enables outbound only internet access. So there's no way to connect to the instances in the private subnet from the internet. However, the instances in the public subnet can do both. You can connect outbound and you can connect inbound. So ideal for running a public-facing web server, for example. So that's it for this video. And in the next video in this series, I'm going to go deeper on network security. We're going to look at firewalls like security groups and network access control lists, stateful versus stateless firewalls, and more.